Yeah, thanks. So I can start.
Oh.
Here. Did you want tea?
No, I'm okay. Just in case I step. Yeah, I have stuff. Yeah.
Okay, now that the card is out, let me start the introduction. So it's really my great pleasure to have today. First, I have to welcome Professor Paola Cappellaro. She's a fourth professor of engineering at MIT, but also professor of physics and nuclear science and engineering, all of that.
Yeah.
And I especially have to thank you to coming here for such a short notice. And she already gave another talk actually at 3 o'clock. So Paola graduated from Politecnico di Milano in a lot of bachelor degrees and masters as it goes all together in 2000. And then after that,
you should not say that. No dates.
Okay, I won't. And then you also have another, and you actually worked on nuclear physics, right? Neutron spectral analysis. And then after that, MSc from applied physics, École Centrale Paris in France, and then she came to MIT. She has done a thesis work with David Corey, which we had here, and those older ones remember many times. And her thesis was on quantum information processing in multiple spin system. So she was doing all the QS pioneering, right, long before this was popular. And then her postdoc was at Harvard, and afterwards joined the faculty at MIT. And she has received many, many, many awards. I'm allowed to read some of them, at least. Air Force Research Young Investigator Award, and then just this year she was named a fellow of APS for groundbreaking contributions to quantum control and quantum sensing with spin systems. So really pleasure to have you here and hear about this groundbreaking work in quantum in sensing of magnetic fields.
Thank you. Yeah, thanks so much for the invitation. And yes, it's better to have it on short notice, so I know that I'm free for sure. So what I'm going to talk about today is generally how we can sense a magnetic field with quantum systems. So I messed up my title, but the idea is quite broad. So I want to talk to you a little bit about quantum sensing in general, and how we can indeed exploit quantum mechanics to make sensing better, and some examples from my own lab. So first of all, what do I mean by quantum sensing? So what we want to do is really to leverage, of course, quantum mechanics in order to have sensors which are better than the classical ones. And by better, I mean both, if you want, because they have fundamentally better accuracy, like, for example, in gravitational wave detectors, but also because they enable new regimes of measurement that you might not be able to achieve with classical sensors. For example, going down at the nanoscale with single qubit sensors. And why one would want to use a quantum system for sensing? Well, we all know that if you have the very famous Schrödinger cat, it's very difficult to observe in reality because any small perturbation will actually collapse the system. This tells us that the quantum systems are very fragile. They are very sensitive to external perturbation. This makes the life of people who are trying to build quantum computer very, very difficult. But if you're trying to build a sensor, actually being sensitive to external perturbation might be a good feature. And this indeed could make a quantum system very, very good sensor. Still, what we want to do is actually to leverage quantum mechanics, so not really collapse our cup, sort of keep it in a quantum state, so that we can indeed leverage correlation and coherence which arise in quantum mechanics in order to achieve better results that are not possible with classical sensors. And there are, of course, various types of sensors, some that really are after this so-called quantum advantage, other which are, in some sense, more practical, where maybe a classical description goes a long way to describe them, even if not completely. And I'm not particularly like orthodox about what to call quantum sensor. We can have a whole discussion about that. If it's somehow quantum and it helps me, I'm quite happy. So how can we use a quantum system, in particular, for example, just a single spin, 1/2, or a qubit embodied in any other particular platform in order to do sensing? One of the simplest ways to do things is to use an interferometric protocol, which, for example, can be a Ramsey type protocol. So the idea is to create some superposition. So in interferometer, this would be like a beam splitter, which creates a superposition state. For spin, this will be like a pi over 2, which creates a state in the equator of a Bloch sphere. So this is what I'm representing with this sphere, the state of a qubit. Then the system will evolve for some time, during which it will accumulate some phase. So this would be an interferometer, the phase which occur in one arm of the interferometer itself. After that, you want to measure. You cannot really typically measure phases directly, so you want to map the phase into a population balance, and you do that by, again, either recombining with another beam splitter or applying another pi over 2 poles to map what is a phase here into a population imbalance between pointing up and pointing down. In general, what you will do is to then measure the probability of being up, let's say in the 0 state, by repeating your experiment m times. So you need, of course, to build some statistics in order to achieve some kind of expectation value measurement or probability distribution. Just a single measurement will just collapse in some random state, so it will not tell you all that much. So we can sort of use the language of quantum information to describe the same things. So this is not your typical quantum circuit, but almost. So you will create an initial state, which is a superposition state, for example, using an Hadamard gate. Then you will have a phase gate during your evolution, and finally some measurements. So again, we can look at this in many different languages, indeed. And so what is the sensitivity of such a scheme? Well, we can have a so-called classical uncertainty limit, so-called standard quantum limit, or SQL. Well, the uncertainty with which I measure the parameter here, my typical parameter is going to be magnetic field, but you could have many other things that you want to measure. So the uncertainty with which I measure is a parameter which leads to the evolution of my system decrease with the number of measurements that I make, capital M, or the number of sensors that I have, b small n. Okay. And of course, because to make each one of these measurements will take some time, instead of a capital M, I can just replace it with the time that it takes for the measurement to happen. So this 1 over square root of t for the uncertainty is the same sort of accumulation that you have in any, let's say, Poissonian process. Classically, your signal-to-noise ratio will improve as the square root of the number of times that you repeat your measurement. So here, this is indeed linked to, if you want, the shot noise associated with the randomness of your measurement. So at the moment, this is, if you want, an uncertainty which does arise from quantum behavior, but it really reproduces the classical one. So how can we go beyond that? Well, instead of just using one single qubit sensor, we can use many. And okay, if I do it in parallel, this again will sort of improve the sensitivity as 1 over square root of n. But I can do something better than that. So before trying to acquire the phase, I can create some correlation among my qubit sensor, in particular an entangled state, my little Schrödinger kitten here. And then your sensitivity scales differently now with the number of sensors that you use. Is no longer 1 over square root of n, but is 1 over n. This is the so-called Heisenberg limit, which still sort of within all the bound of uncertainty principle, etc., but it scales better than what classical sensor could be. So you probably heard a lot about quantum advantage in computing, where you could have exponential scaling with the system size in the speed with which you can achieve some computational task For quantum sensory, we don't have exponential advantage. Typically, there are some schemes which are a bit far-fetched, in my opinion, but you still have, if you want, a quantum advantage which gives a square root of n improvement with respect to classical ones. So how can we achieve this type of improvement? So as I said, here you need to create some type of correlation. These are correlations which are quantum in nature, so really what I'm talking about is entanglement. And of course, if you want to create correlation among your system, among your qubits, you typically will need some type of interactions. Okay? And this is indeed what has been done, and actually one of, to me, beautiful implementation or practical application of quantum advantage has already been shown. And this has been done in the LIGO gravitational detector. So forget about the quantum advantage by Google in computation. This is a real one. So they did something which was practical, at least in this room of physicists. I think that you all agree that detecting gravitational wave is practical. Okay, maybe if you go to the lay person, they will be like, well, it's not so practical to detect gravitational wave. But hopefully you agree that it's a very practical goal. You want to detect gravitational wave better than you could do without quantum mechanics. And indeed, this is what they have shown. Starting in 2019, they injected entangled photons inside their interferometers. These are called squeeze photons. And this really reduces the noise that they have in the frequency with which they measure the photos which are collected, still respecting a certain principle, so the amplitude noise is increased, but the frequency noise is decreased. And very recently, I think a month back or something, they showed that they could achieve the same result at all frequency. Back in 2009, it was only at high frequency. Now they can do it at all frequency. So this really is a practical quantum advantage in sensing. And this is also pursued in other systems, for example, in atomic clock by my colleague Vladan Vuletic. Again, what we're using now are atoms that are used for detecting very precisely oscillations, so measure time in that way. And typically you have, again, this is, if you wanted, the typical picture of your uncertainty, where you have some uncertainty if you're trying to measure, let's say, an angular momentum in the y direction, and also you have an uncertainty in the x direction. The total area here is constant. Okay, this is what the uncertainty principle tells you, but nobody forbids you from stretching out this circle into something which looks almost like a line. So you have now a lot of uncertainty in this direction, in the y direction, but in the x direction now it's very, very small uncertainty. And so you can exploit this fact in order to have better detection of your frequency oscillation of the atoms. And so what they show, for example, here was that they were able to do 15 times faster averaging for the same signal-to-noise ratio without doing this type of squeezing. So before the LIGO, they were injecting, as I said, if you want entangled or correlated photons. Here we were using light atom interaction to create this squeezing, this entangled state for the atoms. Now, if we want to do some, what I would say, more practical quantum sensor, we would like to go to the solid state. Okay, so LIGO is slightly large, okay, for obvious reasons. Might not be so practical. So again, if you are looking for a practical quantum sensor, maybe that's not what you want. These atomic clock, they're much more practical than what we use, for example, for GPS. But again, the sensor themselves are really loud. If you want to deploy really quantum sensor, you would like something which is more compact. So maybe using solid state, it's a good idea. So that is sort of what we would like to do in my lab by using diamond and defects in diamond. Then the question is, how can we achieve this type of interaction in this solid-state system? Okay. So before I come back to that, I just want to give you a very short primer on the type of sensor that we are interested in. So as I say, this is based on defects in diamond, which are called nitrogen vacancy center. Okay? So this is just a nitrogen which substitutes the place of a carbon nearby to a vacancy, which is a missing carbon. and they capture an extra electron, so they in total share 2 additional electrons than the typical carbon lattice. And they, these 2 additional electrons form a spin 1 of electronic spin, which is the one that I map here in red. The defect itself is called a color center, meaning that it gives a color to diamond. And indeed, that's been sought after in gemology for a very long time. But for us, what is interesting is that it emits light. And so we can detect the light coming from a single defect in diamond. And we do that usually through a confocal setup, so that we can really pinpoint the location of individual centers in the sample itself. And indeed, this is the type of thing that we can see if we do precise implantation. Actually, here I'm a bit cheating because most of these holes, these dots, they have a few NV centers. The one which are the dimmest probably only have 1, but all the other one have 2 or 3. What is nice is that because of the energy levels of this defect, we have the ability to optically polarize, meaning cooling down to microkelvin temperature, even if we operate at room temperature, so that our system is more or less almost 100% in the 0 state after about less than 1 microsecond or laser illumination. And also the amount of light that is emitted if the spin is in the 0 state or in the plus and minus 1 state is slightly different. You have about a 30% contrast between the 2. And so we can also detect what is the state of the spin by using a laser light. And this really allows us to do many interesting things. In between the laser illumination and the optical readout, we can manipulate the spin using just magnetic resonance techniques that I hear a lot of you are also using. So here what we are doing is basically what we call a Rabi sequence, where we turn on the microwave on resonance with, let's say, the 0 and I think the minus 1 here. If you add the magnetic field, the plus and minus 1 are sort of lifted in the degeneracy, and you can just address 2 of the levels to have a qubit instead of a qubit. So we drive our resonance for some time, and the spin goes from being up, where it emits a lot of light, to being down, where it emits less light, and we can follow its dynamics like this. If you have a lot of these defects, this is what the diamond looks like. As you can see, it now becomes black because it absorbs most of the light here. We typically use samples which have single spins, so then the diamond itself looks more like this small plate, which is almost white. In terms of quantum sensor, this can be used for many different applications, and it has already been shown, and some of these applications are sort of moving toward like commercialization. I'm very proud that we have an early patent out of this idea of using MV for magnetic field sensing, and it's even been licensed, so I get almost 0 money, but a lot of headache when I do taxes. But okay, it's the pride is a lot, I had to say. So what people have demonstrated that you can do of interest probably to many of you, looking at some condensate matters like magnetism, for example, skyrmions, Johnsonite. There's been some work done in measuring the magnetic field coming out of bacteria which have magnetic property themselves, doing thermometry inside cells. So each one, so this contour here is a cell, and each one of the dots is a nanodiamond containing NV centers, being proposed to detect the dark matter, being used for GPS denied navigation, where you compare the magnetic field that you're measuring with the mapped magnetic field anomalies of Earth to figure out what your location is. We are working together with other groups on using the nuclear spin to detect rotations and many other things. So as I said, like this seems to be indeed quite a practical device for sensing. But if you really want to sort of try to achieve this quantum advantage, it becomes slightly more complicated. So I mentioned that you need interaction. So of course, you might have interaction if you have more than one of these NV centers. But it's difficult to sort of exploit them. So difficult that this is our paper theoretical proposal from 2009, and well, it's not been done yet, so yes, not so easy. But the idea, again, is sort of the concept is simple. So what you want to do is to modulate the interaction of the Hamiltonian through some control so that the spin will interact with each other in such a way to create, indeed, an entangled state. So if you let the spin just evolve under their natural Hamiltonian, they will create correlation, which are, however, very difficult to exploit because they will be somehow in like random direction, if you want. You really want to create an entangled state where you are sort of like increasing the uncertainty in one direction and decreasing in the other one. If that were possible, your sensitivity with the number of spin will have really a different scaling, so no longer this 1 over n, but a much steeper, approximating almost 1 over n behavior with the number of spin. When you go to too many spins, then other sources of noise are sort of overcoming, and your sensitivity, which is the minimum field that you can detect, then becomes larger again. So for the moment, we have not reached this level of control yet, but there has been some improvement. So the first thing that has been demonstrated with collaborator was indeed the fact that we can improve the sensitivity by at least decoupling the interaction among the spins. So without the coupling, as I said, the coupling between the spin will just create some very complex many-body quantum system, which is no longer very good at detecting the homogeneous magnetic field. Now, if you decouple all their interaction, then you can achieve a much denser sample without the effect of noise to be seen, and so you can achieve much better sensitivity. So we hope that indeed building on this work with some more complex sequences to be able to actually achieve this quantum advantage with solid-state sensor. But it's difficult. And so what we have done along the years has been to also work in many other ways to improve our control and exploit quantum mechanics in order to achieve some more practical advantages. So instead of trying to do quantum sensing beyond this standard quantum limit, so to achieve this quantum advantage, we sort of do quantum sensing beside the standard quantum limit. So can we do something with quantum enhanced sensor, maybe using a small system size to do tasks which are not possible otherwise. So for example, we looked at doing quantum error correction by using a few other spins around, again, to improve the coherence time of the system and so be able to detect things for longer. Use additional degrees of freedom in order to store information about what we sense and, again, detect for longer, or maybe look at correlation through this memory storage. And what I'm going to talk today are the last 2 points. So how can we sort of like improve the dynamic range over which our sensor can work? So not only the frequency which are most natural for our sensor, but also like a larger parameter space for the frequency. How can do vector sensing even if you only have a single qubit? And also how we can, again, enhance the coherence time of the sensor so that we can detect for longer and so improve our sensitivity in that way. So these are the 2 points that I will sort of focus on today. So the first thing that I want to sort of talk about is how we can achieve vector magnetometry of a C, so oscillating fields, by using controls. Okay? And to understand that, I just want to refresh a little bit about the modalities that we use to detect magnetic fields. So I mentioned this already. So if you have a static magnetic field, you sort of prepare your spin in the transverse plane, let it evolve for some time, during which it acquires a phase which is proportional to the external static magnetic field, and then you detect it. Another thing that you can do is sort of similar to this experimental data that I showed. If you turn on a field which is on resonance with the energy splitting of your system itself, the spin will start to precess, okay, under this applied magnetic field. And so by how much it is tilted, you can, again, know what is the amplitude of the field. Of course, this detects DC field. This detects fields at the precise resonance frequency, more or less 3 gigahertz for DMV. So there is a lot of other frequency that you might be interested in. One thing that is typically done is to add a pi pulse here. So now you're no longer sensitive to a static magnetic field, but to slowly oscillating field, which are sort of match in frequency with the frequency at which you apply these pi pores. This brings you from 0 to about 10 megahertz. So you still have from 10 megahertz to 3 gigahertz where you cannot detect anything. So how can we try to do that? So to understand that, just a refresher on how we can achieve this resonance drive. Okay. So we do that by applying an AC transverse field. Okay. And I can consider this, of course, as the sum of two rotating fields, one rotating in one direction and the other one in the other direction. So this will be my two fields. Now, what I can do is to jump into the frame rotating with, I think it's the red one, okay, the red arrow. So I jump into a frame which rotates with the red arrow. Let's see if I was correct. Yes. Now the red arrow looks static to me because I'm rotating together with it. And so what I'm left is just like the other field rotated at twice the frequency. Because it's rotating so fast, it will not really affect my system. While now this field, which is static, will indeed affect my system and will drive a flip of my spin. So if my spin is initially up, due to this red arrow, it will just rotate around and will go to the transverse plane and then keep rotating. This is exactly what we do when we do this on-resonance drive for control or for sensing. So we just use this sort of idea of jumping into a rotating frame which will cancel out the other term. Now, if I have a field which is instead oscillating in the z direction, and again, I jump in this frame which rotates around the z direction, what do you think that happens to this field? I should not ask questions. Nothing will happen, okay? Because you're just rotating around z, and the field is around z. So its frequency will indeed be unchanged. And this is what we exploit in order to do vector magnetometry of AC fields. So let's say that now I have an AC field which I want to detect. It is at its own frequency, omega s for signal, okay? And it is in some arbitrary direction in the z and xy plane, okay? So I also add in some additional control frequency, which is the main thing which drives my system. So what I do is to jump into a frame which is oscillating at this frequency omega, okay? When I do that, the component which is around the z-axis is unchanged. You will still have the omega s frequency, while the component of this AC field, which was in the x and y direction, is now seen at the difference frequency omega minus omega s, because I'm rotating in that frame. And so now the two components, the perpendicular one and the longitudinal one, are at two different frequencies. And so I can detect them separately and really reconstruct what is the direction of my field and not only its amplitude. Okay? And indeed, this is what we can do. We can also use some additional trick in order to distinguish whether we have an X or a Y field. But this is indeed more or less the idea is that we will detect by driving the system at the omega s frequency to detect the Z field and drive the system at the frequency omega minus omega s in order to detect the transverse field. So by just changing how we control the system, we can detect the two different components. And this is exactly what we observe in the experiment. So here we choose to work at a frequency where the transverse field and the longitudinal, so the transverse field and the longitudinal field are pretty close to each other, so we could do it just in one single sweep. And we can see that the field was at about actually 28 megahertz, and we still have a little bit of a shift of our resonance, while the other transverse one is shifted by the NV resonance, which one here was just about 6 megahertz between the two. And so we can redetect the X field and the Z field on the same system with just using one single spin and more or less the same control. So we only have to change our resonance frequency by about 6 megahertz. So the additional, if you want, like experimental error that we introduce are more or less the same, and so we have the same sensitivity for both fields by using the same type of control that we have. So we use this method to sort of demonstrate this idea in our very simple system. So here is just a schematic of the system that we have. So we have a diamond with envy centers inside, and we just have a very simple Y that we use to drive and control the system. And we can use that same drive also to introduce some additional magnetic field, in principle a non-magnetic field that we are trying to detect. They're sort of known to us, of course. So this is, if you want, the cut here in the YZ plane. So we have the wire, which will create the typical sort of field lines around the wire itself. It can be considered like as an infinite wire because it's much, much larger than the size of the envy center itself. So then, in order to show that we can reconstruct the magnitude of the magnetic field and also its direction, we scan around to find many different envy centers in the diamond. And for each one of them, apply this vector protocol to detect the field. And indeed, this is what we observe. So for each one of the envy centers, we find not only the magnitude of the field, but also its direction. And we can see that like this arrow here can be then mapped to this circular line of the magnetic field as produced by the wire, which was, if you want, it's upside down. The wire was on top of the diamond, but we plot it at the bottom here. And so we can really use this method to indeed detect this magnetic field and its direction by just using each individual spin to detect the field at its location. Yeah.
Is there an external field in the z direction here, or?
Yeah, so we typically apply about, I don't remember exactly here, let's say 200 Gauss of magnetic field in the z direction, where the z is the N to V axis, so that we can shift the frequency between the plus and minus 1 and just use, let's say, the 0 and minus 1 level, which makes slightly easier because you use two levels instead of being degenerate between plus and minus 1. That's like a permanent magnet, which is chunk put there. Yeah, yeah.
What would you say is the ratio between the static field and the strength of the?
So, I think that this field was on the order of microtesla, while the magnetic field is like millitesla, like 500 Gauss. Yeah. So. So in this protocol, like as I was saying, we were able to detect the vectorial component of an AC field, but we were sort of constrained a little bit on the frequency that we were able to actually detect. Okay, because they should be sort of like around this megahertz type frequency that we can detect with typical method. So we wanted to go a little bit beyond that. So again, recall, if I have this sort of like arbitrary AC field, it gets decomposed in the z direction and the transverse direction, and is shifted in frequency only for the perpendicular direction. Now what I can do is actually to add an additional bias field at a frequency of my choosing, so that originally also the signal field is shifted in frequency. So now the longitudinal part will be shifted by omega b minus omega s, and the transverse part is additionally shifted by the omega 0 of my field. So if I have a signal which might be at a frequency which I cannot measure, let's say 200 megahertz, okay, I can now shift it by just applying a bias field, which is, let's say, 98 megahertz, and just now measure at a very convenient 2 megahertz frequency. A local oscillator. Yeah, it's a local frequency, local oscillator. And of course, then, I mean, like the idea is super simple, okay? It almost looks like just a classical mixer, but you're really using the same system like your qubit, both to do the mixing and the detection. And the nonlinearity really arises from this, like the quantum system itself. It's really the dynamics of your quantum system which introduce this nonlinearity through second-order processes of the system itself. And so you don't need really a classical mixer to achieve this. And so you can still do things at the nanoscale. And if your signal, for example, comes, let's say, from another quantum system, let's say a nuclear spin, typically nuclear spin at low frequency, but let's say it's a nuclear spin or some other source of quantum field, you can still mix it through this quantum system, while it should not be possible to use a classical mixer. So there are like both advantages linked to the fact that you can still operate at the nanoscale, and those advantages because you can mix also a quantum signal, because you're using a quantum mixer to do the mixing itself. And indeed, this is what we observe, okay? So our signal frequency was about 150 megahertz, which again is not a very convenient frequency to be measured. Potentially possible if you add an extremely strong magnetic field, but it becomes very impractical. And so instead of trying to do that route, what we did was to add a biased magnetic field. And so what we can see is that we can, by sweeping this biased magnetic field, we can see a nice dip when we match the target frequency with our driving frequency, capital omega. And we can, of course, see both the plus and minus frequency, some subtraction of the two. So we have two peaks here that we observe. So as I said, this seems like almost trivial, but really this effective field that we obtain comes from analyzing the dynamics of your system through Floquet theory, and actually multimodal Floquet theory, because you have two frequencies. And in some sense, you can consider this classical field sort of dressing up your qubit in the same way that the quantum electromagnetic field will dress up an atom, achieving this ladder, infinite ladder of additional levels. Here we have two fields, so you have two dimensional infinite ladders of level, and you can then achieve transition, which are really a second-order transition by going up in one direction and then down in the other one, which effectively gives this mixing between these two different Hamiltonians here. So, of course, you can, again, forget about everything, just expect from trigonometric function that you will have some subtraction of frequency. But if you do the analysis better, of course, you can achieve better sensitivity of your sensor, because you take into account all the small correction that arise through this second-order process, additional phase shift and so on and so forth, like this AC stark shift, but you would otherwise forget if you were just analyzing your system in a classical way. So really doing the quantum analysis, and this is still an approximation, of course, but you can do like higher order perturbation if you want, if that becomes important, allows us to have a better precision of the sensor itself. The other advantage of this method is that once you have sort of mixed your bias and signal field, now you have typical Hamiltonian that, again, you can find through this Floquet analysis, which are sort of mapped to the typical Hamiltonian that people have used until now to do sensing. And so we can apply many different techniques that people have used in quantum sensing, for example, Rabi sensing, CPMG, which is this strain of pi pulses that I briefly mentioned to detect low megahertz frequency, and just apply to this now sort of like target field, which is the mixed field from the signal and the bias. And so we can just use all the machinery that we know very well, that works very nicely to do quantum sensing now on any arbitrary, almost arbitrary frequency fields. And indeed, we did that, and we can detect both the transverse component of the field, the longitudinal one, either using Rabi-type experiments or these dynamical decoupling experiments, and they have more or less the same sensitivity, and indeed they show the same dynamics as we sweep the time, and the same spectra as we sweep the frequency here. So this, we think that really improves the dynamic range of applicability of our sensor, and we are now working with collaborators at Lincoln Labs to combine this type of scheme with an imaging setup so that we can, if you want, image a different frequency in different spatial point, which can have various applications very interesting, for example, in looking at microelectronics devices and look at the frequency response of these devices through an imaging setup. So this is an example of how we can use, if you want, some control in order to improve our quantum sensors. Another way that, and I will talk very briefly, that we used in the past to still achieve a sort of similar idea to do vector magnetometry now of a static field is to use a little bit of entanglement, like a very tiny amount of entanglement, but to do something that you cannot do otherwise. And the idea there is to remember that the MV center, I already discussed to you, also has a nuclear spin associated with the nitrogen. Typically, it's nitrogen-14, which is a spin 1. And so the energy level, let's say, of the electronic spin 0 and -1 get further split by the nuclear spin. So when the electronic spin is in 0, the nuclear spin only feels the quadrupolar interaction, which splits the 0 and plus and minus 1 level. It has a Zeeman field, but the magnetic field is small, so we can almost neglect it. When the electronic spin is in -1, the nuclear spin also feels the hyperfine interaction, which further splits the plus and minus 1 level of the nuclear spin itself. And so we have this hyperfine interaction, which couples the MV electronic spin and nuclear spin. And we have an intrinsic frequency associated with the quadrupolar interaction, which for nitrogen-14 is actually around 5 megahertz. So we exploited that and the coupling between the electronic and nuclear spin to do this vector sensing, which otherwise is not possible. So how do we do this? So what we would like to do is to sort of replicate again a classical apparatus which is used all the time, which is a lock-in amplifier. So to reduce the noise of a device which tries to detect something at a DC frequency, you typically mix the signal with a local oscillator, okay, which is at a higher frequency, and then you use a bandpass filter, which just let the frequency of your local oscillator go through and rejects all other type of noise. Of course, again, we don't want to use a classical apparatus because then we lose one of the advantages of using this sensor at the nanoscale, which is indeed the spatial resolution. So we want to use something intrinsic. And so we use as this local oscillator the nitrogen nuclear spin, which has this 5 megahertz. And if you really want to quantify its size, it's at about 1 angstrom away from the MV center itself. Okay. So it's really keeping the nanoscale properties of the system. Through this mixing, now what it was a DC field is now shifted up to about 5 megahertz. Also, what was a transverse field now becomes a longitudinal field, which is what we can detect very easily by using these dynamical decoupling sequences matched with the 5 megahertz frequency. And so we can reject a lot of the noise and detect just the signal that we want to detect. And again, this will detect transverse field, which is typically not really possible using, or it's very, very insensitive using just the MV center, by using a little bit of the correlation between the two. So like what this mixing does is, again, to introduce second-order processing between the nuclear and the electronic spin, which are then detected through the MV center itself. And of course, you can combine that with the typical Ramsey sequence to detect the longitudinal part of the DC field and find overall vector magnetometers. This is a figure of a photo of our setup, and this is our experimental result. We use slightly different magnitude of the Z and the X field, so that like the two oscillations are at a slightly two different frequency. But if you look at if you want, the slope and the amplitude of the transverse and it's a bit light here of the transverse field and the longitudinal one, because this is a bit steeper but lower amplitude, this is slower, shallower but larger amplitude, the sensitivity that we found are on the same order. So we can really do this vector magnetometry of DC field with a single spin. So this is, if you want an example, where we use like a very tiny amount of entanglement because you only have 2 spins, so the entanglement is not the same type, which gives you this Heisenberg limit 1/n, because here n would be 2. So, okay, you will have a factor of square root of 2 improvement. Probably will not work too hard to just get that. But by using this small amount of entanglement, you can actually do something that otherwise you cannot do. So detect this transverse DC field with your MV center, to which typically you would be very much insensitive. So this was an example where, if you wanted, the nuclear spin was helping the electronic spin. But we can also do the opposite, use the electronic spin to control the nuclear spin, and then use the nuclear spin as your sensor itself. That's useful, especially if you're trying to detect rotations. So nuclear spin are very insensitive to most perturbation, except rotation. So if you rotate, the nuclear spin will acquire an additional frequency or an additional phase in the same way that any other angular momentum would. Okay, and so that additional phase is the same for the electronic spin and the nuclear spin. But the nuclear spin survives for much, much longer, so, well, you would rather use the nuclear spin. And now with NV centers, you can actually use the electronic spin to mediate the initialization, so how to polarize the nuclear spin. You can mediate the readout to check what the nuclear spin state is, so you don't need big magnets. And you can also use the electronic spin to actually control the system. And this is indeed the type of system that we do. And since you were asking about the magnetic field, you can see one permanent magnet here. There is, and this one is the other one, so they're sort of like sandwiching the 2, sort of like a Helmholtz coil to create a homogeneous field here. These are the 2 magnets there. So we started trying indeed to look at the nuclear spin, but we found some sort of puzzling behavior of the nuclear spin. So we were looking at the decay of the nuclear spin. As I said, nuclear spin should be not affected by much, so maybe the electronic spin, which sits very nearby, should be the main source of noise. But even then, we expect it to not be so strong. And indeed, we have that coherence time, even in very large ensemble of a million of spin, is about almost a millisecond. Okay? But then we turn on the NV to the -1 state, and the dephasing time became much, much worse. And so we were somehow surprised to why it was like that, because that was not what we were expecting. We were expecting that the random flip of the electronic spin due to its own T1 relaxation process to limit the coherence time of the nuclear spin, but that should be much longer than these 2, and the 2 time should be more or less the same. So we started thinking about that, and we were like, well, okay, we have this hyperfine. When your electronic spin is in the plus or minus 1 state, the nuclear spin feels the hyperfine. This is about 2.2 megahertz, which correspond to something almost like a 1 Tesla magnetic field for the nuclear spin. This is like the conversion that you would have. So that's a huge magnetic field. Even if you have a small variation of the hyperfine on the order of 0.03% inhomogeneities in the hyperfine, this would explain these differences in dephasing time. Okay, so maybe this is what we are observing. And for the electronic spin, this hyperfine is 2 megahertz. The electronic spin frequency is 2 gigahertz. So if you have a 0.03% inhomogeneities, the electronic spin doesn't care, and you don't observe it. And so that's why people who have focused on the electronic spin never really observe it. So we're like, okay, let's test this, and trying to look at a modified spin echo where we sweep this time, which really sweep the time during which we are in the ms equals 0 and ms equal -1 for the system. And this is what we observe. So if the hyperfine was really the same issue, then this type of echo would not really help at all, okay? Because, well, you're going from 0 to plus and minus 1, so, at most, you can always be in 0, but anytime that you start adding some small evolution under the plus 1, your dephasing time should become just worse because you add this source of noise. And instead, what we saw was that, yes, when you add a little bit of interaction in the +1, evolution in the +1 for the electronic spin, your coherence time becomes worse, but actually at some point it becomes better, and then it started decaying again. So there is an optimal time of this t, which actually makes your dephasing better. So what's going on? So again, you have to go back to what is the Hamiltonian of your system, where we have both the hyperfine and also the quadrupolar interaction for your spin. And so what happens is that in the MS equals 0, we only have some inhomogeneities in the quadrupolar interaction. While when the electronic spin is in plus and minus 1, we still have inhomogeneities in the quadrupolar interaction. That's always there. It does not depend on the electronic spin state, but we are adding also inhomogeneities in the hyperfine. And it turns out that actually the two have a different sign. And so when we sum them up, we can sort of cancel out inhomogeneities due to the quadrupolar by adding some hyperfine inhomogeneities. And so then we can find the optimal time such that these inhomogeneities completely cancel out by doing the two evolution. And this is indeed what you observe. So if we select that about 20% of the time we evolve under also the hyperfine, this will cancel out exactly the phase which is accumulated due to inhomogeneous quadrupolar. That means that at the level of a single spin, of a single MV center, the quadrupolar shift and the hyperfine shift are exactly proportional to each other. So we are looking at a large ensemble, so in the end we see just decay. But at the level of single spin, you have shifts which goes hand in hand. And this was somehow surprising to us. Okay? The fourth result is that, well, by using this sort of unbalanced echo, as we call it, because it's the typical echo, you put your pi poles in the middle of the evolution. Here, instead, we have to put it at 80% of the evolution. But by doing that, we can improve by 20 times the sort of like the decay time that we have under MS-1 level to up to 3.3 milliseconds. But also we found that this tells us something about the quadrupolar and hyperfine interaction themselves. And indeed, we collaborated with a group of ab initio simulators in order to calculate in simulation what is the expected shift of the hyperfine and quadrupolar as a function of temperature. So we think that in our system, we shine big laser, 5 watts laser, we add microwave to control the system, so we have these constant changes in temperature, and this might explain why we have this shift. And what we observed was that indeed there is an exact ratio of the shift in frequency for the quadrupolar and hyperfine, which is indeed due to the same mechanism. So if you want a theoretical point of view, what we have is that you have a second order phonon effect, which give rise to both the change in quadrupolar and in the hyperfine. So in the end, basically, through this model, we can both improve the coherence time of our nuclear spin and hopefully build a better gyroscope, which is also something that we are working on right now. But we can also learn more about the physical properties of our materials. Of course, this shift that we observed was nicely in line with the shift due to temperature. We expect to have similar but different ratio shift connected with strain and sort of similar phenomena, but again with a potentially different coefficient connected to electric field. So we can use this to sort of try to tease out what type of inhomogeneities we have in our materials. And one direction that we have followed recently was to do imaging in our setup so that we can look at this variation as a function of spatial location in order to try to figure out a bit better what's going on. And we also looked at some charge transport to try to see if this was linked to electric field. So I hope that with all these examples, I sort of show you that quantum sensing, it's a lot of fun, and we are already providing some quantum advantages, and they can also be near-term technology, so we don't have to wait to have a super large sensor with the more intrinsic quantum advantage with Heisenberg scaling, 1/n scaling with the sensor size, in order to really truly exploit quantum mechanics to have better sensor that you would have otherwise by just using classical mechanics. So beyond these Heisenberg limits, even if we have some small amounts of entanglements, can indeed achieve some advantage. I show you, for example, some frequency conversion, some coherence protection. I didn't talk too much about transduction. This is the idea of using two different systems in order to translate a signal that cannot be sensed directly by your sensor into a magnetic signal, which is what we typically detect, using, for example, some additional spin or magnetic nanoparticle. So there is a lot of work that can be done there. The other important ingredient is, of course, quantum control, where you can really exploit a lot of the control theory that has been developed in magnetic resonance over the years and apply to the new regime of quantum sensing to achieve, again, tasks which are otherwise not possible. And we have found that these tools of Floquet, Hamiltonian engineering and Floquet analysis are very, very powerful in order to be able to, if you want, achieve like a good enough analytical approximation, but then we can bring back our intuition on how to control the sensor to move forward. So you could do numerics and have the exact evolution, but achieving that intuition is very powerful in order to be able to really devise new protocols. So this is, of course, overall work in progress, but especially it's work done by my students more than myself. These are sort of a slightly older picture because I wanted to bring up also some people who have recently graduated. And so in particular, I want to give thanks to Yishang, who's now a postdoc at Harvard, and she had worked on this DC magnetic field sensing, which is actually one of the oldest working, even if I present it later. And then in particular, I should give thanks to Chang Gao and to Guoqin Wang, who has done a lot of the work about this frequency mixer and many of the other connected results. And all the other students also have, of course, contributed to especially to many of the other projects. Also want to thank my colleague Julie from the Nuclear Science and Engineering Department, which has become a very strong partner in figuring out many of these protocols and the material properties. So I will leave you with my conclusion and happy to take any questions. Yeah, I think it's okay.
So I assume you will have multiple MV centers, and they will have different orientations in the lattice. So how do you handle that?
Yeah, so, so they have at most 4 possible orientations, so it's okay, manageable. In principle, you could just use the 4 different orientations indeed to do vector sensing. So each orientation will detect the magnetic field components aligned with that. So if you have an ensemble, that's one way of doing vector magnetometry. Here we wanted to do it at the single spin level. So even if you use an ensemble, it's much easier to control the MV which are aligned with the magnetic field. If you are trying to control spins or detect spins which are not aligned with the main magnetic field, either you use very low magnetic field, which then you have to use low frequency. You can only detect low frequency, et cetera, so it's a problem in itself. Or you lose a lot of the optical contrast if you have a larger magnetic field and the spin is not aligned. I guess the shorter answer is the frequency of each spin will depend on the alignment of the static magnetic field to its axis, so we can distinguish the various orientation very easily. But we prefer to just work with the spin which are aligned, or we still want to use all 4 classes at the same time with a scheme which can sort of exploit all 4 of them at the same time, so that you have more sensors in the system. So these schemes would still be sort of useful, even if you were to consider the 4 different classes and applicable. Yeah.
similar of a question, but in NMR, of course. Hello. Okay. In NMR, we use, of course, we work with an ensemble of spins, but it looks like in this case, you only are measuring a very few number of spins, like you said, or am I misunderstanding?
So, like in some of these experiments, just to do things faster, we were actually using relatively large. So here it was, I think, 10,000 spins at least. And that's why we have these inhomogeneities in the hyperfine and quadrupolar. So when you look at the single NV centers, which are also some experiments that we do, then you don't really see. I mean, like in principle, you could have temporal variation, so this is still applicable, but we typically don't perceive too much of a problem in terms of this variation. For ensemble, the heat load that you impose, because you need much stronger laser, much stronger microwaves, so the heat load that you impose on your diamond is larger, and that's why you also have larger thermal fluctuations.
Yeah, so this is done in room temperature, right?
So this is room temperature,
Okay.
yes.
Yeah, so I'm a bit like amazed at how you get such a good signal-to-noise ratio with relatively small number of spins, right? 10,000.
Yeah, so I mean, that's with optical detection. So yes, of course, like we need, like for the single MV, you need to repeat your experiment about 10,000 times or more. But each experiment is about, I don't know, let's say 100 microsecond to 1 millisecond, depending on like how long you want to go. Mm-hmm. So the detection is optical. You have a 30% contrast. So so you have pretty good signal to noise. So that's the beauty of ODMR, optical detector magnetic resonance. Yeah.
Yeah, by optical, I mean, by optical, I'm a bit not sure, because obviously traditionally you use RF coils.
Sorry?
Right. Traditionally in NMR we use RF coils. Well, obviously you're using something different.
Yeah. So this is like what I was. So. Ooh, you have a class. Where is the mic? Yeah. So. So basically, like what we have is that we shine light, okay, and the zero state will just do a cyclic transition, so go up and down, and every time it goes down, it emits one photon. Okay. The plus and minus one state, they also start doing the same, but with some probability they decay down to this so-called metastable level, which is about 200 nanoseconds. So like this process is like 10 nanoseconds. This one is about 200 nanoseconds shelving time. And then they decay down to the zero state without emitting any photons. So if you shine light for some time and you're in the zero state, you keep detecting photons. Right. If you're instead in the plus and minus one state, you keep shining light, but then at some point you don't detect any more photons. So then, as I said, you need to repeat it many times because most of the photons are just trapped inside the diamond and don't arrive to your detector. That's like the main source of problem. But you still like are detecting a lot of photons. So
using photodetectors.
So you use single photon detectors in order to detect, this photon emitted. Yeah.
Right, thank you.
Any other questions? No? Well, if not, thank you very much.